Hello everybody. Welcome to this second lecture on linear systems theory. The first week of lectures we will just learn about writing down or developing models for a given system. So last time we saw a couple of models from circuits till simple mechanical systems to systems which were called the predator-prey models, which essentially were a set of nonlinear equations in the discrete time. So we continue on those things and do a couple more examples related to nonlinear systems. Okay, so one of the simplest examples which we encounter even while we do high school physics is the example of a simple pendulum. So we start with a setting over here where I have a simple pendulum is like a maybe a point mass of mass m, length it's at a distance of L from a pivot point here, and well, so you have gravitational forces, you have damping coefficient over here and so on. Okay, so assume that this is a external perturbation to the system. So the dynamics of the system are well simply given by equations of this form. So my variables here are the angular displacement and the angular velocity. It was x the linear displacement, x dot the linear velocity in the case of a mass spring damper system. So here I am just talking of a rotational motion. So it will be theta the angular displacement and theta dot the angular velocity. Okay, I will not derive the equations for this, which well I presume that you would know these equations, and they are like pretty straightforward to derive. Okay, so just writing down in the state space form. So my states here would be in 2 dimensions. So x would be theta and theta dot, right? So this x1 and x2, if I may call, and these are like belongs to R2. Okay, we will slowly familiarize ourselves with notations of this kind. So what I have here is okay theta dot and theta dot the same. If I write this will be x1 dot is x2. If I map theta to x1, theta dot to x2 and so on. Okay, so in general, so I can write this system of equations as well, the evolution of states x dot is some nonlinear function here. This is called the drift term usually in nonlinear dynamical systems language. This is it's called the drift, and this is the input vector field. Okay. So okay, what do we know about this system, right? So if I were to draw the phase plane, so phase plane essentially is that I am just checking how these two x1 and x2 evolve with each other. So how do I have a plot between theta and theta dot for any initial condition, right? So this will give me the trajectory starting from initial condition here or here or here and so on. So I'll just, so if you do not know phase space, don't worry, I just post some lectures online with the relevant code so that you could run it by yourself. It's kind of straightforward. There's nothing really that you wouldn't know. It's just some consequence of the calculus which we already know. Okay, so let's start with physics here, right? So if I subject these to some external perturbation and assuming there is no friction, what I would see is that well the pendulum will be oscillating forever, right? So that is captured if I look at the evolution of the theta and theta dot, they will just be periodic, right? So, it will just be oscillating forever. So, with a time period defined by the parameters of the system. Okay, if I just look at plot of theta versus theta dot, you see they are just like forming closed orbits, right? So, if I say what happens if an initial condition is here, it will just go around an orbit determined by this line. So, if it's here, it just goes here, you know, around this blue line over here. what if the initial condition is such that theta is 0, theta dot equal to 0, it will just be here forever. It will just be at this point. Okay. If a slight perturbation here, then it will just have a closed orbit here. If I perturb it slightly further, then it will be something like this. Okay, there is a reason why I am doing this. I will just let you know in a bit. So I am just plotting theta versus theta dot in case of what we call as an undamped system. I just have my phase portrait just following some closed orbits. Okay. If the system is underdamped, I know that I start from an initial conditions and my oscillations will die out as time evolves, and then I will just go to a steady state of theta is 0 and theta dot is 0. So assuming I start say an initial condition here, I will slowly spiral to the origin here. Again, if I start at the origin again where theta is 0 and theta dot is 0, I will always remain there. What happens if I perturb it slightly from here till this point? Well, again I'll again spiral back, which essentially means that if you give the pendulum a slight perturbation in the effect of damping, it will just oscillate and the oscillations will die down with time in terms of some dissipation, right, in terms of friction, for example. So for all initial conditions starting from anywhere in this phase plane, I will just go here to the equilibrium point. Similarly, if I have a critically damped case, again I start if I start starting at the origin, I will always be here, and if I am start slightly closer to the origin, I will just again be pulled back to the equilibrium. So the idea here is if I am at the equilibrium point, a slight perturbation will get me back to my original configuration. It is true in the underdamped case. What happens in the undamped case? I am just like revolving around the equilibrium point in some constant orbits or closed orbits. Similar case happens even if I have an overdamped case, just that my response will be slower. So if I start from here, again I am pulled back to the origin. Okay, so this is what we know also from physics, and the model which we develop here actually validates those claims, right. So check for a bunch of videos on YouTube about some beautiful videos on how they mod or how you can actually visualize overdamped, critically damped, underdamped and the undamped case. Okay, so well, this is we know from our high school physics. Okay, things change when I just invert the pendulum. Right? So like it's also called the inverted pendulum, right. So everything else remains the same. I have the mass, the length L, the acceleration due to gravity and so on. Okay, so I write down the equations for the system same as before. My theta and theta dot are as usual, or phi and phi dot are as usual the states of the system. I again have a nonlinear system with a drift term and the input term. The input term just is a constant here, which more generally takes the form g times x. Okay, so what is interesting here is when I plot the phase portrait, right. So again, if I start at theta equal to 0 and theta dot equal to 0, I will always be here. Okay, so if I maybe start at a point close slightly to the left of the origin, you see that my trajectories are actually diverging, right. Okay, we will see the global behavior of this later on, but the initial thing would suggest that they are actually diverging from like the origin. So if I start from here, I might just go here, start from here, I might just go from here. That is also true because take a pendulum is upside down, perturb it, you expect it to go down, right. And where it might converge, possibly it might converge to the downward position, which is maybe somewhere here. So this is like starting from theta equal to phi equal to 0, I might just go all the way till maybe possibly converge to phi equal to 180 degrees. Okay, so that is what the phase plots say here, right. So if I take a damped response of a system, well, this is how it looks like, right. So if I am at the origin, I will always be at the origin. If I slightly perturb, then my trajectories would diverge from the origin. Okay. Now, interesting case is what happens in the undamped case, where here we had closed orbits? Well, see what happens in the case of an inverted pendulum when, well, there is no damping in the system. Well, again I start from the origin and I am always at the origin, right. In the undamped case, I start from the origin, I will always be at the origin. Origin again I mean theta is 0 and theta dot equal to 0. Okay. So, that is a little notational mistake here, this theta and phi are the same. So, I call it theta here, but this is actually a phi here. So, they are the same. Okay. So, if I start close to the origin, well again my trajectories like go away, right. So, here also I start close to the origin, my trajectories go away. Okay, what do they do after they go away is, for example, I start from here, my trajectories go away and they might just be oscillating around the around the point phi equal to 180 degrees over here. So, so if I just perturb it, it might just go down all the way here and might just keep on oscillating here. So, that is captured also in the phase space over here, right. So, over here. So, you can see that if the initial condition is somewhere here, then if I perturb it till here, it might just be oscillating around this orbit here or this orbit here. Okay. So, what is the observation here? So, first is that if I just let me take an underdamped case for a simple pendulum, a slight perturbation around the origin will get it back to its original configuration, right. So, over here slight perturbation, I again come back to the origin. Okay. Now, what is the origin here? So, these are also called as equilibrium points of the system or even the steady state conditions. Okay. So, here slight perturbations will restore the system's configuration to the origin, whereas here slight perturbations might take the system away from its original configuration, they might go somewhere else, right. So, this kind of behavior where slight perturbations from the origin make the trajectories diverge is usually called as an unstable behavior, whereas if I go back to this case, so this is actually called a stable behavior. Okay. So, another thing about nonlinear systems is about equilibrium, right. So, you can have multiple equilibrium points. So, we will talk about that slowly when we learn about linearization of nonlinear systems. But for the moment, so the idea was just to show you two different versions of pendulum, how the models change and how do we even analyze the behavior of the model via the phase space. Okay, so more in the modern context, right, we all talk of networks, social networks and everything emerging, that the maybe IoT is also a large network system in the world, things originating from cyber physical systems and so on. So, let us see what can we, a very simple example, right, which a bit of electrical engineers would know, and also maybe this is of interest to other domains. For example, say pollution monitoring, which is neither an electrical domain or it is a kind of a multidisciplinary problem, right. So, let us talk of this simple example on sensor networks or more like wireless sensor networks. Not to the details of this, but just to give a little introduction to what these sensor networks are supposed to do. So, these are used in applications where we wish to collect and aggregate information over a region. So, what do these sensors or sensor networks do? They collect information, they compute and then aggregate all the measurements with some special distributed sensors, and these have their own computing and transmitting capabilities, right. So, typical examples would be if I just want to monitor temperature of a region, so I just put a temperature meter over here, maybe the thing might be slightly different 2 kilometers down the line and so on. So, how do I evolve at a certain number saying that the temperature around this region is say 32 degrees or the humidity is 50%, air pollution, carbon monoxide levels and so on. Okay, so let us see, well, how do I model this, right. So, before even I build a sensor network, I maybe equip it with all the computation and communication aspects. So, even before I do that, what do I need to be careful of, right. So, what is important is that if I put this say 5 temperature meters across a region, so do they reach consensus about the temperature, that the temperature of this region is say 32 degrees. Now, how can we model the time evolution of this information, that I just put it at t equal to 0, different things might give me little different initial temperatures, maybe 32.1, 31.8, somebody might give me 32.5 and so on. How can we model the evolution of this, or to reach a consensus for a temperature or humidity in an area? Okay, one model equation or one thing is based on the concept of linear averaging. So, I just took this example from this beautiful book on network systems which is available online by Francesco Bullo. Okay, so let us come to this expression a little later. Just look at a very simple example. Say I have these 4 networks or these 4 nodes which constitute a network. The graph of which looks like this, that 1 is connected to 2, 2 is connected to all others, 3 is connected to 2 and 4, 4 is connected this way and so on. So, there is no direct connection between 4 and 1, 3 and 1 and so on. Okay, so, if I were to look at see the evolution of the measurements here, I just say look, so what does this algorithm mean, that xi, which is some state that I am measuring, is the average over xi, which is the individual measurement, and xj for all the neighboring nodes. Okay, let's see what this means in this example. Say take this x1 for example. So, if I look at the average of xi, that is x1 itself plus all its neighbors. So, what are the neighbors of 1? That is just 2. So, I just say x1 plus x2 over 2. Okay, that will be how the evolution, right. This is x1 plus for the next time instant. Say look at say for example x4. x4 would be well x4 itself and its neighbors. What are its neighbors? Its neighbors are x2 and x3 and divided by 3. This will be the next at the next time instant, right. So, how the evolution depends. So, I just write this averaging this algorithm, what is called the linear averaging algorithm for all the nodes, and I say get a model like this, that x at k plus 1 should be a k here will depend. So, x1 will be like this 1 over 2 x1, 1 over 2 x2. Similarly, this is connected to all the nodes, so it will have 1 by 4, 1 by 4 and blah blah blah. So, this will be the model of it. Again a discrete time model where I call this as again xk plus 1 as axk, just for notational purposes I call it the A of this sensor network in this example. Okay. Now, okay, what after this? So, what am I interested in? Does each node converge to a value, right? So, is the value same across all nodes? What does that mean? So, do the set of agents reach a consensus about a certain property, about about a temperature or humidity, or maybe in some sense even in social dynamics, say some opinion building. Now, does that value depend on the initial conditions? Well, can I just look at it and say, so what does it mean about convergence? Does it converge to a value? So, I just want to say what happens say as x k plus xk as say k goes to infinity. Starting from initial condition, give me x0, I can compute x1, now give me x1, I can compute x2 and so on with this, just with this expression, right. Give me any x, I can compute the next one. What happens for larger values of time? Does this matrix have any hidden information? So, what one way is to look at, okay, look at this matrix and just keep on computing, right, until I reach maybe I can just say for powerful computer and say let us compute a power 100, say a power 200 for example, and say well does it reach to a consensus value or not. Do we want to do that all the time? Well, the answer is no. Now, can we evolve at some methods based on this structure of this A that will tell us all the hidden information that we or all the questions that we wish to answer. Okay. So, it turns out that if I compute this A power k, so why does this A power k come here is simply because of this, right. So, if I say what is x1 is A x of 0, x of 2 is A x1, this is A square x naught, similarly x3 would be A cube x3 and so on. So, therefore, if I look at the time evolution, I am just interested in computing the powers of A square, A cube and so on. So, convergence will at infinity, I am just interested in computing this. Okay, but I don't really know how to compute this, right, even with any powerful computing tool. Okay, but then are there any properties of this matrix, right, that I can make use of it? Okay, we will not do the proofs or anything of this. Well, first let us read down the statements. Okay, if this A is primitive, which means, okay, this should be greater than 0, not 2. Okay, if A is primitive, which means does there exist a number k for which A power k is positive, which means all entries are positive. Okay. So, if this happens and if the matrix is row stochastic, what does it mean by row stochastic? If you sum any of these rows, the sum of these rows would be 1. You add these 4 numbers, it will be 1. Add these 3 numbers, it will be 1. Add these 3 numbers, it will be 1. Right? If these two properties hold, again we will not do the proof of this. So, I am just to give an introduction to what kind of properties that we are looking at exploiting. We are just not interested in writing x dot equal to Ax. There is much more to that than just rewriting a transfer function into a state space. Okay. So, in this case what happens is there is a nice theorem which is an extension of the Perron-Frobenius theorem. It's all beautifully explained in this book if you are interested in the details. It says the following, that if these two things are satisfied, you can see that in this example you compute A square and it will be greater than 0. You can just do this as a very trivial exercise. So, this is satisfied and it is row stochastic, which means all the rows add up to 1. In this case, the limit or the convergence algorithm says something like this, that as k goes to infinity, A power k converges to this number, where 1n is simply something like this, 1, 1, 1, 1 n times. Okay. Now, what is this W? The W is the left dominant eigenvector of A with eigenvalue 1. Okay. Not really, we are not interested in how to compute this, what is the dominant eigenvalue or something. So, the idea here is to show you that there are some hidden properties of these matrices which we can exploit to solve the problem at hand, right. So, in this example it converges, or it happens that the value of each node just converges to this one. You see this, so all x1 will be 1 over 6 x naught and x1 naught and so on, right. So, it will be same through all the 4 nodes. So, node 1, node 2, node 3 and node 4. So, much of the aim of this course would be to learn, equip ourselves with tools which will help us solve problems pretty quickly. So, what is a tool here that I exploited? The tool here is just this statement here, right, which comes from linear algebra, that if this matrix is primitive and row stochastic, then I do not need to worry about anything. I can just blindly copy that tool into my application and say, yeah, yes, there actually is convergence of the algorithm and each node converges to a particular value given by this. And it has a very beautiful dependence on the initial conditions. Okay. So, slowly we will learn tools like this. So, the idea here is to just give you an introduction to what are the kind of tools that we need to learn here. They may not look, you may not maybe buy them off the shelf on Amazon, but okay, we have to import that from some literature on linear algebra. Okay. So, another interesting class of systems are what we call as hybrid systems, and as the name itself suggests, that these are mixture of some kind of continuous time dynamics and discrete events. Okay. So what are continuous time dynamics? So far we learned there could be like x dot equal to ax. In the discrete case, you will have xk plus 1 is a x k plus 1. You can have in the nonlinear case x dot equal to fx and so on. Okay. So in this hybrid dynamics, what happens is that, well, these are the response of the system, well, in the continuous case just governed by f, or here just governed by a or a and so on. So here the response is governed by not only f, but also how they respond to certain discrete events. Okay. As a simple example, I am just looking at a temperature control system, a very simple example of a thermostat. We learn it in very early training of our physics education. Okay. So what I am interested in is temperature control of a room. Let us say I am in this particular room, I want to set the temperature to 24 degrees. Okay. When I enter the room, say the temperature is 28, I switch on the air conditioner, it will cool it to 24, and once it reaches that 24, saturation 24, it will switch off, right? It does not need to cool it further. Then you see a rise in temperature from say 23.9, again it will go to say some number 24.1, it will again switch on, right? So you have a discrete states here which will tell if the air conditioner should switch on or switch off, right. So that is the discrete event here, that or the discrete state or the discrete variable that governs my system. Then you have of course a continuous variable theta t. So my state now evolves according to a nonlinear or maybe a linear equation also, which is defined by x, which is the current state or the state itself. Then you have maybe certain external influences like people entering the room or changes in the conditions outside the room and so on, and a certain switch. So if I am in a comfortable, so if I enter the room, I want to switch on the AC for the temperature to go to 24, my dynamics will take this pattern, right. So I will have x dot is f of x with the switch in the on state and some presence of disturbances or external influences. So if I am on the comfortable region, my AC will switch off and then the dynamics will go according to this one, right. So you have the continuous dynamics are not only depending on themselves, but there is a discrete event that is also guiding them here. Okay. Again, we will not really investigate into details of this. There is an infinite amount of literature within the hybrid systems community. You can also think of some other examples like a bouncing ball. When the ball is you just release it from a position here, so the natural evolution of it would be through the acceleration due to gravity. Once it goes down, it might just again, so while this upward movement will depend again on the restitution coefficient, the friction losses at the impact and so on. So you have a continuous model when the ball, until the ball hits the ground, and another continuous model of the reaction of the ball as soon as it hits the ground, and the discrete event there is hitting the ground. Okay, I will not do the example of that, but okay, you can, it's available in plenty in any literature. Okay, one interesting thing which I thought I would do here is on the system of multiple collisions. This is important because, well, if you look at much of our JEE training or training those days, they talk of elastic and inelastic collisions and so on. Okay, now can we revisit those in a different way than what we were taught of in those days? Okay, so let's do this simple example. This is also called a Newton's cradle, and there are like beautiful videos online which you can watch about this. So I just start with 3 point masses, say Q1, Q2, Q3. Say these are positions Q1, Q2, Q3, and each of them moving with some velocities Vi, right? So this is V1, V2 and V3, and some force functions which possibly are acting on them given by this one. This is again nothing, right? This is just the Newton's second law written in terms of the state space form, or in terms of two differential equations, that the rate of the position is the velocity, rate of the velocity again is related to the force. Okay. Now, assuming that the masses here are just unit masses. So the m here is it does not appear. So m is equal to 1. Okay. So a typical motion, what you would expect is, okay, so this would hit once they hit, then you have a motion which is 3 goes this way, 3 will come back, hit 1, and then you just follow this process. Okay, we will see if we can have an explanation to why this kind of particular motion happens. Okay. So, under what conditions do collisions takes place? So, if I look at Q1, Q2, Q3, well, collision will take place when Q1 and Q2 are just at the same position, Qi equal to Qj. It is point masses, so I can actually quantify this quite nicely. And then if the velocity, if they are moving in this direction, if the velocity of V1 is greater than velocity of V2, then collision will happen. Okay. Now, what do we know from physics? Well, this is a very standard thing, right? Conservation of momentum, that the total momentum before impact is equal to the total momentum after impact. If I call the velocities before impact as V1 and V2 and after impact as again Vi, V1 star and V2 star. Okay. So, how do the velocities change? Well, there will also always be some restitution coefficient which might lose velocity depending on if the collision is purely elastic, purely inelastic, something in between and so on. Right. Okay. So let us start with this, right. So, let us say at time t equal to 0, I start with this, right. So maybe I am at time equal to 0, I am something like this with the velocity here being 1, 0 and 0, just say maybe just before collision. Okay. So, in this case what is happening is that the left mass is colliding with the center mass. And of course, there is also the mass in the center which is in contact with the right mass. So, this will collide with this will collide with this. So, what are the ways of modeling this phenomena? Okay. So, one way is that I look at this as say a mass 1 here, this is my Q1, and I take the remaining 2 masses as something as of mass 2, and let me call this say velocity of this is V1. And this is the combined velocity of 2, 3, right. So I am just looking at collision of two bodies with a mass 1 and a mass 2, and the initial velocity is V1. The impact rule, like you can just simply substitute, just use these to derive the rule saying that okay, V1 plus, which is just after collision, and V2 3 plus will take this form, right. So again all the masses are 1, right. So these expressions are easy to derive. So in case of a perfect elastic collision, well, we can expect this, right. So the velocity of this guy changes and this guy becomes 2 by 3 and so on. And similarly in case of a perfect elastic collision, right, when E equal to 0. Okay. So I think we know a bit of this physics, so we will not delve too much into the details of this. Okay. Now, is this the only way to model? I can also look at it as of a multiple collision where the left mass first collides with the center mass and then the center mass then collides with the right mass. Okay. So, I am looking at again 3 distinct velocities V1, V2 and V3 just before collision and just after collision. Okay, so I will not do this case, this is pretty easy to derive, but what is interesting for us is the case of E equal to 0 and what happens in the case of multiple collisions, or here we have events of multiplicity 2. So, one event is this guy colliding with this guy and the next event is this guy colliding with this guy. Okay. Now, this is interesting, right. So, what will happen in case of a perfect elastic collision? Okay, so then again I rewrite these collision rules. Okay, there are some typos here which we will take care of later. So, if I rewrite this collision rules, what I get is this one, is an expression like this. Okay, what does it mean? So, if I say just let us derive it just for the first one, right. So, I have V1, V2 and V3 for the first collision. If I rewrite this one, so Vi minus Vj, or if okay, say V1 minus V2, what is E equal to 0? So, this will be 0, this is say just after impact. Okay, that will be the first rule. Second rule will tell me okay, M1 V1 plus M2 V2 is this. So, I will have M1 is 1, so V1 plus or star plus V2 is again V1 plus V2. Okay, and then you keep on writing this and then you just arrive at a general expression like this. Okay. Now, with this defined conditions, this will give rise to infinite events. Infinite events would be, okay, this will collide with this will collide with this, come back, collide, and then so on. Now, how do the velocities change in this case? This turns out to be pretty interesting. So, at event 0, or when okay, just before the collision, I have V1 to be 1, V2 is 0, V3 is 0. Okay. Now, in the when the first collision happens, when the left and the center collide, then I have this, the velocities will be 1 by 2, 1 by 2, just by this formula here. It is derived again from those two impact laws. Okay. Now, in the second event, what happens is that the center and the right collide. So, okay, this guy, okay, so nothing will happen to this velocity, but then I am looking at events between these two. Okay. So, the velocities will just be half of it, so it will be 1 by 4 and 1 by 4. Okay. The next event would be when, okay, so we have left colliding with the center, center colliding with the right. Okay. And then now next I have a transfer now between the, so this guy stays as it is, and then V2 and V1 collide on the other side. So, I will have the velocities again going by this formula, and I keep on doing this. At infinity, I will have velocities converging to 1 by 3, 1 by 3, 1 by 3. Okay, you can actually derive this, right? It's you can do this as a simple exercise. Okay. So, what is happening? So, this is in the event of multiple collisions. I am looking at E equal to 0 at steady state, if I may call so, that my velocities will be 1 by 3, 1 by 3, 1 by 3. Okay. Now, let us go back to this situation where we had considered the collisions to be as if that a particle of mass m is colliding with a particle of mass 2, where these two other point masses were like clubbed together. You see this one, right? They are actually the same, right? Okay, think of it, of why this happens. So, the outcome of this event with multiplicity, so you have infinite events, so of which I call it as the event of multiplicity infinity is the same as method 1 with an event of multiplicity 1. Okay, think of why this happens as we do a few more examples in the next lecture. Thanks for watching.